Good morning, everyone. It is currently 5:45 in the morning. I have not gone to sleep yet, and I'm covered in amniotic fluid, which means, drumroll please, it's a boy. Last night, 10:15 p.m., Mr. Slagle became a daddy. That's pretty amazing. That's pretty awesome. I'm excited. Yeah, we got birth things going all over the place, which means it's a perfect time to do algebra. Here we go. Here I have a geometric sequence. You can tell it is a geometric sequence because, full screen, okay? Because as I go from one term to the next, let's get it off eraser, shall we? As I go from one term to the next, the pattern is I am continually multiplying. And I'm continually multiplying by the same number. Now, looking at these fractions, it's a little bit harder to see than looking at from 3 to 9, but it is the same every time. I'm multiplying by 3. 1/9 times 3 is 1/3. 1/3 times 3 is 1, and so on and so forth. Okay, this thing that we're multiplying in each step is called the common ratio. The common ratio is, in this case, 3. Hooray, okay? And then you needed to remember that the terms in the sequence, this is a sub 1, a sub 2, so then a sub 5 is the number 9. 1, 2, 3, 4, 5. Cool. So the things that you need to find the explicit formula for a geometric sequence are the first term, which is 1/9, and the common ratio. That's one way to do it. Now, keep in mind, when you're reviewing for this final, you don't actually have to do it this way. You can just say multiply by 3. If it asks for the 10th term, just sit there and multiply by 3. That is sometimes easier until you get to the 10th term, so you'd have to do it 5 more times. In this case, to get to the 8th term, which is what your homework asks for, I'm currently on the 5th term. Multiplying by one time would get me the 6th, so multiply by 3 is 27. And then one more time is 81, which gives me the 7th. And one more time is 243, the 8th term. But let's do it with the explicit formula so you know. You could always multiply it like that. Here we go. Let's find a sub 8. A sub 8 is equal to, well, let's do the general case. A sub n is equal to a sub 1 times the common ratio to the n minus 1 power. That's the pattern for a geometric sequence. You start with the first term, you multiply by the common ratio n minus 1 times. The reason it's n minus 1 is because to get to the third term, you're going to have to multiply twice. It's always 1 less, right? So now let's do a sub 8. A sub 8 is equal to a sub 1, which is 1/9 times the common ratio, which is 3. 3 to the n minus 1, but n is 8. So 8 minus 1, guess what? 8 minus 1 is 7. So you end up with a sub 8 being equal to 1 divided by 3 squared times 3 to the 7th over 1. Woo! Okay, multiplying across the top and bottom, you end up with a to the 8th is equal to 3 to the 7th divided by 3 to the 2nd, which is 3 to the 5th, doing top minus bottom powers. And 3 to the 5th is 243, just like I said. Okay, now be careful. Some of these geometric sequences, thank you, Christina. Okay, some of these geometric sequences are look like patterns that are dividing. So if you say like 10, 5, 2.5, what people are tempted to say is that the common ratio is 2, and it's not, because 2 is not what we multiply by. We are multiplying by the reciprocal of 2, which is 1/2. So you'd have to use 1/2 as your common ratio in that instance. So for this, for the first group of questions, you're finding the common ratio in the 8th term by any method you choose. The next group, I've given you a set of points, and I want you to find the equation for the exponential function that travels through those 3 points. Now this is made quite clear if we put it into a table. Let's make a table of our x and y values. Okay, our x values goes from -1 to 0 to 1. Okay, that means we're increasing by 1 each time. That's nice. So we should see then kind of some sort of a pattern in our y values. We start at 1/2, it goes to 2, and then goes to, my goodness, apologize, folks. That is supposed to be an 8. That's what happens when you make lessons at running on no sleep for 24 hours. Okay, so it should be 1/2 and then 2 and then 8. Now, if you'll see, we're multiplying from here to here by what number? Well, it's the same here. We're multiplying by 4. Okay, that's our kind of common ratio. And the equation that I gave you was, well, I mean, it is. Exponential growth is the same as a geometric sequence. That's how they change. So there's kind of our common ratio that's telling us how we're growing. And I always said that whenever x is 0, that's always our starting value, okay? So that means with our graph, right, you're starting here at 0, 2, and you've increased, when you move over 1, you've gone up a ton. 3, 4, 5, 6, 7, 8. You've increased a whole heck of a lot. In fact, we've gone to precisely, let's go down to 1/2. We're going to 4 times the height. 1, 2, 3, 4. 1, 2, 3, 4 times the height. So our curve is an exponential growth that looks like this. Now, here's the trick. The equation for an exponential function is always y equals a times b to the x, where a is our starting value, okay, and b, this is our common ratio. How do you find a, the starting value? Well, that's the one with x equals 0, right? And then you really just take this number. So this equation in our exponential form is y equals 2 times 4 to the x. If you plug in 0, you get 4 to the 0, which is 1. Anything to the 0 power is 1. 1 times 2 is 2. If you plug in negative 1, you get 2 over 4. You'll get 2 to the 4 to the minus 1, which moves the 4 to the bottom, right? And you'll get 2 over 4, which is 1/2. And you'll see some more of these examples in the next. So that's kind of how the process works there. Moving on, let's do a couple graphs so you guys can get used to that. All right, so the first one we're going to graph is going to be really basic. It's y equals 2 to the x. So here's my technique for this. Basically, you just sit here and plug in powers of x. You're going to pick a power and test it out. So I always start with 0 because I think it's the easiest. X to the 0 means y is equal to 2 to the 0. Anything to the 0 power is 1. So the first point that we've got is the point 0, 1. Boom. Okay. Now we try x equals 1. X equals 1 creates 2 to the first. 2 to the first power is 2. 2 to the second power, that's why I'm starting at this 2. 2 to the second power is 4. This kind of looks like a quadratic shape until you get to the next one. Okay, that is not on our graph. Ignore that dot. Delete it. Okay, the next one is 2 to the third power. 2 times 2 times 2 is 8. Okay, that is not a parabolic growth. It may look like it, okay? And the funky one, so let's do that one real fast. X to the third equals y equals 2 to the third, which is 8, so that gives us the point 3, 8. Woot! Okay, now let's pick a negative value. What happens when x is negative? This is where people usually get confused. When x is negative, it goes back to that basic exponent rule. You get y equals 2 to the negative first power. Negative exponent means that that base is on the wrong side of the fraction, so we leave a 1 in its place and put 2 to the first in the bottom. 2 to the first is just 2, so it's really just 1/2. Basically, the pattern is, as I go this way, I'm taking the previous value and multiplying it by 2. That's my growth factor, so to speak. And as I go backwards, I'm really kind of dividing by 2. And half of 1/2 is 1/4, and half of 1/4 is 1/8. And what we've got here is we've got a line approaching 0 that never actually gets there, while this thing kind of shoots off to infinity and beyond. And this line that it's approaching, x equals 0, has a name. It's called an asymptote, a $10 word. Okay, cool. That's terrible. I'm still working on using this pad. It's kind of hard. Okay, that was an easy one. Let's do a more challenging one. That's how you graph. The next one is going to be, oh, by the way, this represents exponential growth. Okay, this is growth. As I'm going from left to right, the graph is increasing, right? Exponential growth. It really has to do with the fact that the thing that's being raised to the x power is bigger than 1. It's exponential growth because of that. Okay, next one. Y equals 10 times 1/2 to the x. Okay, notice that the value that's being raised to the x power, 10 is to the first power, times 1/2 to the x. That value is less than 1. Okay, so what happens when we start plugging in numbers? You guys can try. X equals 0. See if you can beat me to the answer. Y equals 10 times 0.5 to the 0 power. Anything to the 0 power is 1. This puts us at 10. 0, 10. Whoa. Okay, that's kind of crazy. All right, I don't know what this was. That was way high. Let's try another point. This is crazy. X equals 1. X equals 1 means you have y equal to 10 times 1/2 to the first. Well, 1/2 to the first power is just 1/2, so this is really 10 times 1/2, which is 10 over 2, which is 5. So at 1, you're at 5. So it looks like as I'm moving to the right, now I'm multiplying by 1/2, right? I'm doing half of the previous value. Half of 5 then is 2.5. And half of 2.5, as I move again, is 1.25. And half of 1.25 is 0.625, which let's say is right about there. So as you can see, I'm just doing half of the previous value, and it's getting closer and closer to 0. As I'm going down the line here, I'm getting closer to 0. I'm decreasing as I move from left to right. That means this is exponential decay. When you're graphing these, please don't put like 2 points. I want to see it launch off your graph this direction and get really, really close to a value over here. Okay, last one are these word problems. This one says the number of feral cats in Hawaii is growing by 9% per month for 2 years. If the starting population is 17,000 cats, how many will there be in 2 years, assuming there's no limitations on space or food? The general equation for exponential growth is this. A of t is a function of time, okay, is equal to little a times 1 plus r to the t. Okay, now all these are different things. Big A, you need to remember this is all in your notes. Big A is the final amount of cats in this case. Little a is the starting amount, or the initial amount of cats. Okay. 1 has to do with the fact that we're basing it off the amount of cats that we have. We are either increasing or decreasing, and we're going to add or subtract our rate as a decimal. This rate has to be as a decimal, and it's tightly related to time. Rates have to do with time, right? So if the rate, notice our rate says 9% per month, but the time says 2 years. We got to make those things match up, okay? So if we want to figure out how many feral cats there will be in 2 years, well, we want to know the final amount, right? So we say A of, and we're not going to do this in years because the rate is in months. We're going to have to convert 2 years to months, so we'll say A of 24 is equal to our starting amount, which is 17,000, times 1 plus 9% as a decimal is 0.09. That is positive only because it says Hawaii is, the number of feral cats in Hawaii is growing. That's why we add 0.09, and I have to turn 9% into a decimal. And then the number of time periods. That's 9% per month. How many time periods? We said 24. And now you follow the order of operations, which means we work on the inside of the parentheses first. We do nothing with 17,000. We add those two together and raise that to the 24th power. 1.09 to the 24th. So I'm going to bust out my calculator. Get that baby done here. 1.09. Whoa, that's a lot of feral cats, folks. Okay, so the amount that it's grown, you take 17,000, the starting amount, and you're going to multiply it by this growth factor, which is 7.9 approximately. So you do 7.9 times 17,000. The amount of feral cats on Hawaii after 2 years is 134,488 cats. About. Let's do a squiggly equals. Let's see if I can draw one. Oh yeah. I'm pretty good. Nice job. Okay, wow, I'm way tired. Hey, thanks for watching. That's a quick review. Hopefully that was helpful on how to do these questions. You can expect a review of other questions in the future, so please use this as a resource as you're studying for your final and as I am having baby time. Alright, I miss you guys already. Kind of. Okay, hope to hear from you soon, and I hope to be back soon to see you guys before the end of the year. Okay, bye.